So you can think of there being a Ti, right. So I have specified the states where it will be active in. So whatever is there in the state space which is not there in SA is basically Ti, and Ti are the states it will terminate in. Okay. In fact, they have made a specific dichotomy like this, so it essentially means that if you are in a terminal state and call an action, call a subtask, it will not move. Basically, it will just return. Right. So because it's not in the only in the active states do I specify actions. If I am in one of the terminal states, I won't specify actions. Right. On the contrary, in options, right, the same state can be in I and the beta. Right, in options the same state can be in I and beta. So I can start a option in a state, there might be also some probability of ending the option in that state, right. But if I start the option, I will take at least one action. So that is the thing. So if I start from here, I will not end here, I can take an action, go somewhere else, right, and then but if I come to this state while executing the option, I might also terminate here. Does that make sense? Right, I have some state. If I start an option here, then I will certainly move out of the state. Okay. If I start an option, I will certainly move out of the state. But while executing the option, if I land here, I will stop. Okay. So there is a little flexibility in the option definition that allows you to do that. Okay. Any questions? Okay. So now let us take a look at value functions. Right? How do value functions work here? So you recall what I said, right? These are essentially a collection of SMDPs. It's a collection of SMDP. So let me take one of those, right? Let me take Mi, right? So we have Si, Ai, Ri hat, right? So for the Mi SMDP, the SMDP corresponding to Mi, so I have the states, right? So I have the actions, right? Do I have the rewards? Ri hat plus Ri, R, right? The original reward. The two both together give me the reward function for the SMDP. So Ri hat, Ri bar plus R gives me the rewards for the SMDP. So the SMDP corresponding to Mi. So I have Si, Ai. Right, what about the P? Huh? P is a little tricky. So now P I have to define this joint distribution, right? So if I only take the okay, I apologize. Yeah, so we will come to that also. What's that? Where are you getting the array bar from? That is the task specification, right? When I specify these MIs, those are the things I have to specify. I have to specify Si, Ai and array bar. Okay, just like options, we have to specify the even option policy. In HAMS, you have to specify the structure of the machine. So in MaxQ, we not only specify this graph, right? I mean, this graph is implicitly specified there, right? The graph is drawn from these AIs, right? So that's basically you have to specify Si, Ai, Ri bar for every task. Okay.
So the -5 that you get for going
plus
to
5.
the wrong destination.
Oh, okay, wrong destination.
-5 and +5, those are part of the core MDP or the MI?
It has to be part of Ri bar, right?
Array bar. So then, so only the -1 that you get every time step is part of the core MDP. There's nothing else.
Maybe when you drop off the passenger, you might get a reward. The task is for you to drop off the passenger at the goal, right? So for dropping off the passenger at the goal, you might get a core MDP reward. Or for doing a wrong pickup, when you try to pick up a passenger when there is no passenger, or when trying to pick up a passenger when there is already a passenger in the car. So these are, doesn't matter which subtask you are doing this in, these are all wrong.
Dropping at the wrong position should be also part of the core.
It's part of the core MDP. So regardless of which subtask you are doing this in, it will be wrong. So that's what. So picking up at the wrong location, dropping at the wrong location, all of this are bad. And like he was saying, if you want to make sure you are getting a smooth ride, you can also penalize it for running into obstacles. That will be in the core MDP. Huh?
Obstacles will have high negative reward.
What?
Obstacles will have high negative.
Could possibly. I mean, that's what I'm saying. If your goal is to have a smooth reward, smooth ride. Otherwise, what will happen? If you run into an obstacle, you will get a -1 anyway. So you will try to avoid running into obstacles, because every time step you get a -1, right? Whether you move or not. If you run into an obstacle, you don't move, so you get a -1. So if you want to really avoid going anywhere near an obstacle, then you can give it a high negative reward, so that you, well, basically you can't reach any of the goals, because you have to go very close to an obstacle to reach the goal. So you have to think about those things. Yeah, that's fine. Anyway, so what about the transitions and the rewards? I've erased the rewards also, because that was incorrect. What I wrote was not correct. If AI, the AI that I pick happens to be a primitive action, then all of it is fine. So essentially it's a core MDP transition, right? And then the core MDP reward function for taking that action. But if I happen to pick another subtask, right, a non-primitive action as my AI, right? Not AI. AI is the bigger thing. So the AI that I pick at this time instance is a non-primitive action. So what will be my transition? So now I will have to define a probability over, right. So n is the number of time steps it is going to take. S prime is the final state you are going to land up in. S comma A, right. So I will have to do this for task I. Huh? What's that? N is the number of steps it will take to complete.
It's a random variable.
Yeah.
It's like tau in the.
Yeah, if you want, I'll use tau. The same, it's a dummy variable, right? So if I use tau earlier, I'll use tau now, right? I mean, Dietrich uses n, so I used n again, but we can use tau. It's exactly like tau. In fact, now it is tau. Okay. So how will you determine this? This will be determined by how many time steps the subtask corresponding to A will take to complete. Okay. So this is determined by MA, where MA is the Ath machine here, the Ath subtask. Correct? Are people on board? Okay. Now what about Ri? You know all about Ri. It is a summation of the rewards that you are going to get while the actions corresponding to A are being executed. Right, there will be the MA will run, right. So the policy in MA will now run. When I call A, I am going to execute a policy. So for every step along the way, I am going to get some reward, right. I am just going to accumulate that. Okay, that is essentially what my Ri will be. There will be a discounting factor depending on how you are doing it. Right? If you want to use discounted rewards, use a discounting factor. Right? So the tricky thing is, what should Ri be? Think of the MDP definitions. What is Ri? It's a reward expectation. So what I just described to you was a sample. You have to convert that into expectation. You have to write out the proper transition probabilities and other things in order for you to define that, right. So it turns out conditioning on S prime and tau is a little tricky, right, when I write these reward functions. So I can write it without conditioning on S prime and tau. So that is the expected reward for taking action A in state S, right. So this is the expectation of this summation given that I started in state S and I did A as my first action and I followed my policy pi, right. So now it is a little tricky. So this expected reward that I plug in to solving Mi already has the policy pi there. So because I need to know what is the policy I am following below Mi for me to compute this reward. Right, because I have called A here, but then A might call some other action A prime might call some other action A double prime, right. So for example, root I might have called pickup, so but pickup might call navigate and navigate might call south, right. So that might be the one action that gets executed, maybe it finishes navigate, then it will come back to pickup and then it will come back to root, right. So I basically need to know what was the entire policy that was executed for me to compute this expectation, right. So I will condition it on the whole pi. This is reward for I. Sorry? These are the rewards for the core MDP, you are right. Right now I defined it as the rewards for the core MDP. In fact, I can.
Sometimes we can even replace them with this RA if we go for a sub.
Which one? The RA hat, RA bar.
Yeah.
So that is one tricky part because RI bar will be defined on the states of this MDP, right, this SMDP. Well, these small transitions that I see here might be transitions in the smaller in the SMDP below me, right. So they might not correspond to the states here, I mean they might correspond to a different set of states, correct. So they might correspond to different set of states, so it is not entirely clear to me that this thing can I can assign a pseudo reward to every step along the way. Right. So what I should possibly do is add a separate term for our pseudo reward here, and so that I construct my entire reward function. So this will be the core MDP rewards because these are coming from the subtasks below me, right. So during the execution of subtasks below me, then I could potentially add a pseudo reward. See, right now I am going to remove the pseudo reward because it adds a lot of complications. So most of the development that I will show you now is without the pseudo reward, and how do you do the corresponding things along with the pseudo reward, I am going to ask you to read the paper. Essentially you will have to maintain a second value function throughout. So one value function which actually uses only the core MDP values, core MDP rewards, another value function which is used only internally to the subtask which uses the pseudo reward as well.
Pseudo reward value function chooses which one of the pickup, drop off or navigate.
Sorry?
The pseudo reward value function chooses which one of the pickup, drop off or navigate to choose.
No, that is a core MDP reward function. Pseudo reward tells you, well, if you are in pickup, right, to successfully complete the pickup task, you use both the core MDP and the pseudo reward, right. But finally when you want to solve the problem, but you do not use the pseudo reward of navigate while you are trying to solve the pickup task, that is the difference. When you are trying to solve root, so what will be the pseudo reward of root? Nothing, because root is trying to solve the original problem. So the reward for root should be the core reward function, right. So reward for root is the core reward function, and it will never use the pickup pseudo reward while solving this, right. Likewise pickup will never use navigate pseudo reward, navigate will never use pickup pseudo reward, right. The pseudo reward is limited only to that subtask for which you have defined the pseudo reward, okay. So just ignore the pseudo reward for the time being, we'll come back to that later. Right. So what I am going to do now now that we have some kind of a definition for the SMDP, okay, let us start writing down the value functions, okay, then we can worry about how will we learn those value functions, right. So, that is essentially what we are looking at. So, I am going to use the following notation. So, I am going to say V pi I comma s is the value function of state s in task I, right. I mean I could have done I here, right. I could have said it is a value function corresponding to task I mean I would have said that is a more natural notation, but I am not putting I there, I am putting I here because that is the way Dietrich defined it. So, it is easier for you to follow when you look at the paper later, right. So, what do you think this will be? So, you want to do Bellman style writing up, right. How will I do this? So, I will say first say pick the cost corresponding to the first action you are doing, right, which will be let us say pi, right. So, that will be the first action I am doing, right, and then right. So, that is like the Bellman equation. So, what is missing here? The summation over pi. Why is it missing?
Already chosen a policy pi from below.
I heard something, some other murmurs also. Let us see if someone gave a right answer. Why is the summation over pi missing? Oh, come on guys, wake up. We did a version of this already. Because I am assuming pi is deterministic. That is why I wrote pi s. Heavy lunch today. Noticing too many people with half glazed eyes.
Summation over A that is missing.
Summation over A that is missing. Yeah, fine, whatever. A is summation over A pi s A. Yeah. Why didn't you say summation over A is missing?
Trying to see
I don't
what
know.
is pi.
Yeah.
We are trying to figure out what pi is it? Okay. Just say summation over A is missing. Okay. Just because you are assuming it is a deterministic policy.
And so will it not depend on whether it can go into state I instead of state J instead of I?
Why?
In the next
What is next?
going to a different SMDP.
Why would it go to a different SMDP? Because I am just looking at the value of state S and
Particular subtask.
I.
But say at a particular state it calls state calls SMDP MJ.
Uh-huh.
So will it depend on the value function of that MJ?
No, he is right. So, there is just too much notation in MaxQ. So, one of the things which I should have introduced earlier. So, we have value functions corresponding to the actual policy pi, right. So, we will have value functions corresponding to actual policy pi, and so that is going to look at the entire execution of the policy, right. So, I am going to call define something called the projected value function, which looks at the value function only for till the completion of task I, right. So, I am only worried about task I finishing, right. I am not worried about what happens after task I, right. So, this is the projected value function. So, and what we are writing here is the Bellman equation for the projected value function. Okay. In fact, in a later paper somebody pointed out that there are problems with the MaxQ architecture, the way the MaxQ value function decomposition, the way Dietrich defined it, precisely because he operates with the projected value functions. And because he operates with the projected value function, there is no chance of you learning a hierarchically optimal policy. So they came up with a different kind of value function decomposition that allows you to choose to learn the recursive optimal policy or a hierarchically optimal policy, but you needed to have a different value function decomposition that did not just operate with the projected value function, but it had something that came after the projected value function also. I will explain what in a minute, but what we are talking about is a projected value function, and you are right that I am only worried about till the task I completes. I do not care about what happens after I. Okay. Sorry. Right. Now, given that caveat, is it all clear? What is happening here? Right. But what is this guy? Not pseudo reward. Think about it.
There is expectation over the entire reward that is accumulated over the task.
Yeah. Over which task?
This subtask.
I
The ith subtask.
No. The pi ith subtask, pi I of s, right? I would have taken some action there, right? So the entire reward I accumulate over the execution of that action should go in here, right? And what is that quantity? You don't look here. Look at the notation we have introduced already here. Right. So, it is a value function in that projected value function in that subtask. So, what is a projected value function? It is the total reward I accumulate till the end of that option, the end of that subtask, right. So, now what happens when I call pi I of s, it will run till that completes and then it will come back. So, what is the projected value function in pi I of s? It is essentially the reward I accumulated till the end of pi I of s, right. So, similarly I can write in subtask I, what is the value function s comma a, and this is even clearer to write. This is essentially right, do not get confused. Now I have flipped a and s, this is why I said I do not like this notation. If I had written a here, it would have been very clear, right. So here you have sa, here it is as, that essentially means it is the value of state s in subtask a. Just like this is value of state s in subtask I, this is value of state s in subtask A, right. And then what else do you have? Essentially has the same thing. And you want to write that last term in terms of q. What will I do? This is q pi. So I have now Bellman equation for v pi and a Bellman equation for q pi. Okay. So sometimes, not sometimes, so what we do this, we define, man I am really off color today. So we call this thing the completion function C. It's a little confusing here. So C pi of ISA is the cost or payoff or reward that you are going to accumulate in subtask I after you complete action A starting from state S. right. So, look at the way this works, right. I have completed action A. Once I complete action A, I will be in some S prime. So, I am looking at how much reward I am going to accumulate from S prime till the end of subtask I. So, the completion function exactly says that. So, I started A in state S. After I finish that, how much more reward will I get till the completion of subtask I. So, that is called the completion function. So, I can write my Q function as so my Q is essentially V plus C. Right. So, C is equal to this. So, V pi A comma S equal to right. So, Q pi is this, V pi is okay. You didn't okay fine, you didn't sleep and fall over or anything. Okay. So, V pi is Q pi of A S pi S if it is a composite action, basically like one of the subtasks, right, and it is primitive action, then it is just the expected value of the reward, just because I made this into AS, right. So, this is essentially in what is the value of state S if under primitive action A, which is essentially this, I am marginalizing over S prime, right. So, this will be what is the value of state S in subtask A, right, which is essentially the Q function. So, now you can see kind of it goes recursively, right. So, I want to compute the Q, so I need the C, right, but for computing the V, if it is a composite action I go down and ask for the Q of the lower action, right. If it is a primitive action I return this. So, it is some kind of a hierarchical thing. So, if I want to okay. So, I can make you really sweat by saying okay, here is the value of state x in 0.
The pi over there that you have written in Q pi A S, is it pi A of S or pi I of S?
At least somebody is awake, not me. Good. Right. So, how will you write V pi O of S? First let me define some notation for you to write this out. So, I am going to say pi is composed of right. So, any policy pi that I define is a hierarchical policy and it composes of pi 0, pi 1, pi 2 up till pi k, which are essentially the policies I will be following in each one of the k subtasks, right. I have m0 to mk. So, pi 0 is the policy I will follow in m0, pi 1 is the policy I will follow in m1 and so on and so forth. So, pi is written out like this, right. Now, I want you to write out the value function for state S in subtask 0, right. So, how will it look like? So what will happen is pi naught will call some other action below it. First action it will call is something below it, right. So let us say it, the first action called by pi naught is A1, correct. So what I will essentially do is I will get, I am going to write it slightly ulta so that it is easier for me to keep adding terms to the end. So what should I have? V pi 0 would be q pi 0 s comma A1, because I said A1 will be the first action I take, right. So pi a of s will, pi 0 of s will be A1, let us say, right. So q pi 0 comma s comma A1, right. And then what do I do? I add the, right. So I will essentially, for that I will have to, for computing that q function, what should I do? 0 comma s comma A1, so that will be v pi of A1 comma s plus c pi of c pi of 0 comma s comma A1 plus right. Now let us say that I go into A1, okay, and let us say for sake of ease of writing, the first action I take in A1 is A2, okay. So now what will I do? It is a composite action, right. So v pi A1 comma s will be q pi A1 comma s comma, which is A2, right. So q pi a comma s comma A2, right, and then I will go back to q pi a comma s comma A2, I mean A1, sorry, A1 comma s comma A2, which will be v pi A2 comma s plus c pi A1 comma s comma A2. All the pi's will be pi, right. These are all conditioned on the whole policy that I am executing, right. So pi naught of s is A1, pi 1 of s is A2, right, pi 2 of s is A3, that is what we will say.
Subtask will be choosing that pi I.
Yeah, within the subtask I will be choosing the pi. Then what will come here? It will essentially be v pi of A2 comma s, right. So like that I will keep going until I hit a primitive action, right. So if I want to compute v pi 0 of s, so essentially I will look at what the action I pick is, right. I will make a query, I will look at the completion function for that action, then I will go down, look at the completion function of the choice made in the subtask, then if I reach the end, then I will just use the v pi, right. If I reach the, I am sorry, if I reach the end I will just use this expression, right, otherwise I will use the q and I keep going, right. So this is essentially what the value function decomposition. What is the nice thing about it is, if I take A2, right, for some other subtask also, right, say here I am looking at v pi 0 comma s, right, suppose I look at v pi 0 comma s prime, right. So there also I would have learnt this c pi, I mean this is the same c pi that I will be using regardless of how I come to the end. I may start from s and go to some state, I may start from s prime. So well I have to learn different this thing, but the point is, yeah, if you go further down the hierarchy it makes more sense, not in the root. So if you are further down the hierarchy there could be multiple ways in which you could have started the subtask, right. I would have learnt the same completion function, I can just reuse the completion function everywhere. Likewise I can reuse the yeah, so if I am caching the q function I can reuse the q function also everywhere, right. So essentially what this allows me to do is break down the value function, right, into chunks of rewards, right, which I am likely to see again and again, right. Each chunk corresponds to executing a subtask. right. So that is essentially what value function decomposition does, and yeah, so we are already getting into confusions, right. This really all is a pretty complex setup already without bringing it to the pseudo rewards. There are no pseudo rewards already the completion function and this becomes a pain. So if you look at the root task, right, everything is good. In the root task what did we have? So we had the completion task, a completion cost or the completion function after you finish A1 starting from S for completing the root task, what is the reward. So that is all fine, right. But then if you go to a sub level, so what is the completion function here say? Only for completing A1. I do not care what happens after A1, right. But in reality if I want to learn something hierarchically optimal, right, I need to know what is going to happen after A1 if you think about it, right. So it is not enough for me to get out of the door, I need to know what happens after I get out of the door so that I can decide which door to get out of. Right. So I need to know what happens after the completion of A1 also. So what was proposed as a modification was a second completion function which was for the whole problem, right. But then it becomes tricky, how do you maintain this across the entire structure, right, how do you maintain this consistency. Essentially it is like passing on information from some subtask very far down the line all the way up to the first subtask, right. Suppose I am executing subtask 1 and my task ends after subtask 100, then whatever happens till 100 all that information has to be brought back to subtask 1 for me to define the second completion function, right. So how do you do efficient bookkeeping? So that is essentially the problem that they had to solve for learning hierarchically optimal policies with the MaxQ. So right now you can define these kinds of completion function, and now you can define a Q learning SMDP Q learning variation, right, where at every subtask you update the Q value for the subtask as well as the completion value, right. So you do not update the Q value of the subtask, you just keep calling down till you reach a primitive action. So you basically have this, right, as we saw here, right. So I can keep calling down until I reach a primitive action. So I have not yet reached a primitive action here, but if I reach a primitive action then basically all I have is this, right, and this I do not know because this assumes that I have knowledge of P and the knowledge of this expectation. So what should I do for this? Maintain some kind of a running average or something, right. So essentially that is what you will be doing. So if you hit a primitive action you return that running average, so otherwise you keep querying. So all you really need to store is that running average, which is essentially the Q function, the Q value, right. If you think about it, the running average is essentially the Q value for taking action A in state S, right. What is this? The Q value for taking action A in state S, right. This expression I have written here, the original Q value, no SMDP Q, nothing, the original core MDP Q value for taking action A in state S. So it is QSA, is that right? Yes or no? No, yeah, Q value would have the future expectations, right. So it is just the expected reward for taking action A in state S, right. So that is all this is. So you basically compute the expected reward for taking action A in state S, and that is one thing that you have to remember, and apart from that what else you have to remember? For every action you have to remember the completion cost. So what you now you basically define an SMDP Q learning variation where you update the completion cost at every state, right, whenever you take an action, and whenever you come to a primitive action you update the expected reward. Whenever you take a composite action you update the completion function, whenever you take a primitive action you update the thing. So essentially that is roughly what it will reduce to. So there is something called MaxQ 0 learning, right. So MaxQ 0 learning is for the cases where the pseudo reward is 0, right, uniformly 0 for all subtasks in all states the pseudo reward is 0, then you have MaxQ 0 learning, which is essentially what I described to you. You update the completion function and the expected reward, and that is basically it. Then you have MaxQ Q learning, which is defined for arbitrary pseudo reward functions, where you maintain 2 completion functions, one for solving the subtask, one completion function which you use for picking actions in the subtask, and one completion function which you use for answering queries from above, right. So, when pickup asks navigate give me your completion function, navigate will send the function that was learnt only with the core rewards, but when navigate wants to know the q values to pick an action, it will use the completion function learnt with the pseudo rewards. Okay, make sense? So, you have to, but then the bookkeeping becomes more painful. So, you have to make sure you are updating the right q functions, right completion functions throughout. So, that is essentially what MaxQ learning is all about. Okay, so yeah, we are done with MaxQ today.